distribution. Here we see the results of the distributions of the predicted probability for each of compound based on the classification of being positive or negative, but also for the compounds that contain missing data, except for DNT, where we didn't have any missing data. One type of the output that such a model can give to us is this classification into 3 levels of high, medium, and low probability that a chemical can induce DNT. Because our data set had more than 70% compounds being known to induce DNT, most of the compounds have a high level of probability, few medium level of probability, and fewer low level of probability to induce DNT. Another kind of information that such a model can provide, especially useful in terms of decision making, but also to communicate the risk associated with a compound, is to look at the probabilities that have been computed for each compound independently, and especially to understand how it follows that biological path. In our case, the reduction of this brain-derived neurotrophic factor that leads to the other 2 key events at cellular level with the adverse outcome of DNT. And as we can see, it started at 71%, it follows 99%, 99%, and then 100% bisphenol to be predicted as to induce DNT. Importantly is that here we see the Bayesian credible interval, also known as highest density interval. This is this interval that describes the uncertainty around that predicted probability. And we see this is, here it is quite large. And once we add layers, biological layers, and we incorporate more details, the final predicted probability becomes much more stronger. I'll continue with the last methodology that we've developed, and that's about investigation of the possibility to quantify a linear LP based on literature. And for that purpose, we've chosen the linear LP for Parkinsonian motor deficits, which is a well-developed LP, and it's also endorsed. And we assessed the references cited in this publication of the OECD for quantification appropriateness. This assessment has been done following several criteria that have been predefined in order to evaluate for the presence of quantitative details. 26% out of the references cited were descriptive studies. 56% were experimental studies, but not for rotenone. We wanted to quantify and to investigate this LP specifically for rotenone. Then 50% of the data of the references were cited for rotenone. However, there were maybe phenotypic type of studies or not multiple concentrations being tested, not multiple time points. And as a result, only 3% of the total number of papers we considered and we proposed to be appropriate for quantification purpose. However, I have to mention one important aspect. None of these publications were developed at the time having in mind an LP construction. It's rather about fitting somehow the data in order to be able to evaluate an LP. Well, this exercise allowed for recommendations on how to design appropriate testing strategies, also to identify where additional efforts are needed, and allowed us to model a few quantitative key event relationships for a demonstration purpose. Herein are the 3% of the references that have been finally evaluated and that contain any quantitative data. As you can see, these type of studies are ex vivo, in vitro, in rat, in bovine heart, in human. And also, as you might notice, the key events at molecular and cellular level were evaluated mainly in vitro, while the key events at organ level and organism were evaluated ex vivo and in vivo. Therefore, there is an opportunity for the use of human-induced pluripotent stem cells there is also an opportunity for the development of a battery of in vitro tests that can allow us to evaluate this biological path for rotenone and other compounds that binds to complex 1. Now, in terms of quantification, we managed to combine the data that were of in vitro studies conducted in humans, and those I'll show in the next slides the graphical representation of the model, which consisted of key event 1, key event 2, and key event 3. So inhibition of complex 1 leading to mitochondrial dysfunction and impaired of proteostasis. The data allowed us to combine the results of concentration response for 3 time points, 4 hours, 24 hours, and 48 hours. The key event 1 had one functional toxicity assessment assay conducted, while the mitochondrial dysfunction, the key event 2, was tested for multiple functional assay. And then the final key event 3, impaired proteostasis, was also tested for one associated biological effect. Now, these concentration responses and responses were fitted for the best curve, and we used different tools, available tools for that. For example, DCR in our language. It can also be used ProAst or benchmark dose modeling of the US EPA. The LL4 states for the type of regression that was best fitted, and the number 4 or number 3 states for the number of parameters that were included in that mathematical function. And the best fitted curve was chosen based on the ACACA information criterion. Well, besides the need for more and more QAP models, we need as well frameworks to assess and to increase the trust in the applicability of QAP models. And one way of increasing this reliability can be by evaluating the level of confidence in the computational approach utilized, as well as in the qualitative understanding that the QAP model describes. And hence, when we think of computational approach, we might think of the structure that it uses. And here we can also mention mathematical equations. The parameters, as for example, I shown within the Bayesian model, where we used a hierarchical approach. The data itself, because a QAP model is data-driven. On the other hand, we have this qualitative description of AOP, and thus there is an opportunity to use semi-quantitative, quantitative weight of evidence analysis to quantify the level of maturity of that AOP, for example, in a scoring system, and thus to evaluate the evidence for stressors, for key events, for key event relationships. Well, all of these 3 methodologies have been applied externally and internally within the N3 project for any other endpoints. For example, one of the projects is led by Leoni for the development of AOP networks for nanoparticles. There is another ongoing project led by Zara for an AOP for impairment of angiogenesis. We were also happy to know that the work was uptaken by several stakeholders, including the UCD, and rather personal statement. I hope one day a QAP model in combination with physiological-based pharmacokinetic and quantitative structure activity relationships types of models will provide a basis for non-animal chemical risk assessment. With that, I would like to thank you for watching this presentation, and I would like to thank all the amazing scientists I had the privilege to work with. The N3 Consortium has been a platform that any PhD student would want to have access to, and I'm very thankful to Paul, Ellen, Maxime, and all my colleagues, ESRs, and all PIs for all the productive meetings we had and all the discussions and great memories. I'd like as well to acknowledge my participation at the workshop at the Lawrence Center in Leiden in Netherlands for the funds received for attending that workshop. And especially I would like to thank Dr. David Pamies, Dr. Dan Villeneuve, Dr. Ivana Campia, Dr. Stefan Scholz, and all other participants that based on the discussions we had during that workshop, we were able to develop the conceptual framework for quantification of a simplified version of the AOP network. I would like as well to acknowledge Dr. Junpen Lao from Google Research, who made one of my dreams coming true, and that's to learn a probabilistic programming language and to be able to apply it in toxicology. I would like as well to acknowledge my secondment at the Joint Research Center and to thank to everyone who made it possible. I would like to thank Dr. Andrew Orff for his support and supervision during the secondment, as well as the collaboration that continued and it still continues nowadays. I had the pleasure to work with Dr. Annabelle Price, with Dr. Brigitte Landesman, with Dr. Clemens Witter, and many thanks to Dr. Maurice Vellen. I would like, and most importantly, to thank my research group in Liverpool. It was a great pleasure to work with each of you, to share all the moments together. I would like to thank Dr. Judith Madden and Dr. Stephen Enoch for their support and continuously time that I received through the past years. And I would like especially to thank my supervisor, principal investigator, Professor Mark Cronin, for his support, for his time, for all our discussions, for setting an example on how science should be done. I'm very thankful for this experience. Thank you very much to everyone.